in the next case, I will be copy the same circuit, and in the next case, what I do is I will not go with the increasing the pull-up network. As we know, the formula of the gain is increasing the pull-up network. That is the solution we have followed as of now. But we have a problem that increasing the resistance is leads the collector current, and it leads to the transistor going to the saturation region in one situation. So I will not increasing this one. I will decrease this one. So what I do is, for decreasing the pull down resistance, I cannot reduce this one. If I reduce this one, the stability of the circuit will be disturbed. So I cannot do this one. What I do is, in parallel to this one, I will be keeping a capacitor. We call it as a bypass capacitor. I will be keeping a bypass capacitor over here. So with the bypass capacitor, I will be having a flexibility. With the bypass capacitor, I will be having a flexibility. So whatever the signal it passes to the resistor, whatever the current it passes to the resistor, right, now it is getting bypassed through this one, right? So the resistance will be totally bypassed. So the effective resistance across this branch is limited. So effective resistance across the pull down network is reduced. Obviously the denominator term is reduced. Obviously this term will be totally increased. Now if I keep the capacitance over here, it is around like 100 micro. So because of this coupling capacitor, bypass capacitor, now let me observe the gain. Now as we observed, right, in the previous case, not even 4 divisions my signal couldn't be spread, but now the signal is going to be shared among more number of divisions. If I reduce the strength of the each division, I can observe this one. So this is what my new signal. Yes, this is what my new signal, right? One thing before I do is, because of this resistor, transistor is deviated from the active region. So what I do is, I will be making the resistance value less. I will be keeping 3 over here. I will be keeping 3 over here, right? 3 over here. Yes, because of 3 kilo parallel with the 3 kilo, right? So the overall resistance over here, it is 1.5. So when we keep like resistance of small value, it may pump my maximum current. It may pump maximum current. So the transistor again will try to come into the active region, right? So now from this one I can observe the transistor in the active region, right? Now I will observe that output waveform once again. So this is how without distortion I could get the output, and let me calculate the output over here. Let me calculate the output over here, where from this one if I calculate 1 division, second, third, fourth, fifth, there are around like 5 divisions into 500 milli. So each division is 500 milli into 5 is around 2500 milli. That is the strength of the output we got it. So now if I update the value 2500 milli, that will be the output. So now if I calculate the gain, so 2500 by 20, it is around 125 gain we got it. 125 gain we got it. So previously we could improve the gain by 2 times, 2.5 times, not even more than 2.5 times. So transistor alone cannot improve the gain. So here the beauty of the circuit is, individually the capacitor came into the picture because of the coupling capacitor. So that pull down resistance value is reduced. So this value is reduced to 10 ohms, around 10 ohms. Pull down network value is reduced to the 10 ohms. That to the 10 ohms because of the emitter resistance of the transistor. So once it is reduced to the 10 ohms, so that 1.5 kilo ohms by 10, it will be around like 150. So we got it around 125. So approximately we got the gain is around. So if I update the value for reference, that pull up network value is 1.5 kilo ohms. Pull down value is very small, it is around 10 ohms. So the gain of the circuit will be around 150. The emitter resistance over here, it is 10 ohms. It is calculated over here. With that I calculated the gain and we got the gain around 150. So the value of 150 need to be expected as a theoretical one. Practically we got it nearby, it's around 125. So as we observed, there are around like 5 cases we discussed. As 5 cases one by one it's saying, when you are trying to increase the pull-up resistance values, the gain obviously it will be increased, but there is a limit where the because of the resistance the transistor may go into the saturation. So what my solution is, not only going with increasing the pull-up resistance, there is another option, decrease the pull-down resistance by keeping the capacitor. So once I keep the capacitor, the gain is increased to 2 times, 2.5 times. Now it is increased to 100 times, like more than 100 times that gain is increased by only capacitor. So these and all cases we call like a C amplifier without bypass capacitor. This is the case where C amplifier with bypass capacitor. So we came to case 5. We came to the case 5 and we got the gain around 125. Right. So now let us copy the same case and we'll go with the next case again. We'll copy the same case once again. So in the sixth case, what I do is, as of now I was worried about increasing the gain itself. But while I'm increasing the gain, I couldn't consider other parameters. So now I will go with another parameter called phase shift. Is my circuit is going to give the phase shift of 180 degrees or not? So now if I see that this is my output, I'll be moving to the 0 position and I'll activate my input signal also. If I zoom it, time scale, if I change it properly, I can observe that input signal and output signal will be in the opposite phase, right? Where like positive half cycle, it will be overlapped with a negative half cycle. We wanted to see it properly, you can pass the simulation and using these scroll buttons, right, where I can see the waveform in which position you want. So now this is the input and output are in 180 degrees phase shift. Now what I do is the capacitance value over here it is changed to 10 micro. 10 micro. So let me do the simulation once again, update my simulation. So here if I see, let me pass and let me bring the waveform into the middle. So here that input waveform and output waveform is not in not in opposite phase, not having 180 degrees phase shift. So my requirement is not only increasing the gain, parallelly we have to consider the other parameters also satisfied or not. As C amplifier will be giving 180 degrees phase shift, if the circuit is failed in giving 180 degrees phase shift, we are getting the gain is not enough for us. So here we have to remember that keeping the bypass capacitor, due to which maybe you increase the gain, maybe increasing the gain, but whatever the value you want to keep it here, it is not we cannot keep it. We have to calculate the value of the capacitance over here. So because of the capacitor there will be a frequency response and there will be a pole formed in the frequency plot, in the Bode plot. Based on the pole we have to calculate the phase shift over there, angle formed by the each and every pole. There you have to calculate the range of the capacitance. So that range should be more than 100. If I keep that range again to the 100, if less than 100, there will not be giving the phase shift around 180. So if I keep more than 180, more than 100 microfarads itself, if I do that simulation once again, then only, sorry, so then only we will be getting 180 phase shift rate. So let me repeat this point once again. When I keep the capacitor over here, I am getting maximum gain. But while getting the maximum gain, parallelly I have to check whether my phase shift offered by the circuit is 180 degrees or not. So for that sake, I have to know the range of the capacitor. Below 100 microfarads, the capacitance cannot be kept over here. If the capacitance value is more than 100, then only you can accommodate, you can keep the capacitor, can be used for us to increase the gain. So that is what our fifth case. And increasing the gain, as of now, in 4 cases we have, in 5 cases we have. Now in the sixth case, we need to know the range of capacitor. So because of maximum range capacitor around 100 micro, we got the gain is maximum along with the phase shift also 180 degrees. So this is the sixth case. Let us go with the next case. Finally, as of now we calculated the gain, observed the gain, and we observed the phase shift also. Now in the next case, I will be observing the bandwidth. So for that I will not use oscilloscope. I will be taking border plot over here. So I can see border plot will be here, and border plot dedicatedly there is a input channel and output channel. So input channel of the border plot is connected to the input of your circuit. And output of your border plot is connected to the output of your circuit, and negative terminals of your input and output of your border plot is connected to the ground. So after like border plot is connected here, so let me simulate it once again, and let me see the frequency response plot. It will be increased, and there will be a constant response. We can see it in the mid range, and there will be a roll off again at high frequencies. So in the mid range I have to see the frequency response plot, flat frequency response I couldn't see here. What I do is, there is a vertical and horizontal range I have it, the panel range I have it, I can increase it to some level, to 100. If I keep it, I can see the frequency response in mid range also. I can see it over here. Now if I keep my cursor over here in mid range, I will be getting the gain is around like a 42 dB. As of now gain was calculated in normal, like it is now calculated in terms of dB. So now for this one I will be updating the gain over here in dB. This one is not required. I will remove. So here, so gain, we got it 150, 125. So in dB if you calculate the value, it will be around 42.04 dB. In terms of dB, this one normalized gain is this one, in terms of dB is this one, right? So now what I am trying to do is, I will be calculating lower cutoff frequency. In the sense, the frequency at which the gain fall by minus 3 dB. 42 minus 3 dB, 39.04. Yes, is around 39.04, and where the frequency it is showing, it is called lower cutoff frequency. So from this I will be updating lower cutoff frequency. From this lower cutoff frequency FC1 is equal to, it is around 153 Hz. So this is the amplifier which I have it, will be giving the gain around 125 for the range of frequencies above 153. So above 153, whatever the signal we have it, all range of signals will be amplified by 125 times. So your signal will be audible up to 125 ranges, let us suppose. So now I will be doing some modifications in this circuit. Now, as of now, pull up resistance value is changed, pull down resistance is changed, bypass capacitance value is changed. Now I will be changing the coupling capacitance value. So in this case, in the last case, I will be changing the bypass capacitance value. In this case, I will be changing the bypass capacitance value. So the bypass capacitance value is kept at around 100. This capacitance value is kept around 100. So as I know, the gain will be depending upon the pull-up network or pull-down network. Yes, it is not depending upon the coupling capacitance. So if I do the simulation again, and if I see this one, it can be clearly observed that the gain still it is 42 dB. So it was like around 42 dB when we keep the coupling capacitance around 10 micro. Now also it is giving the same value, 42 dB itself. Now if I calculate the lower cutoff frequency, 42 minus 3 dB, 30. So now when I keep capacitance coupling capacitance value 1 micro, as we know the formula of cutoff frequency 1 by 2 pi RC, so theoretical value of the capacitance is equal to 1 by 2 pi RC. As like a C value is reduced, cutoff frequency will be increased. So from this one, when C value is reduced, that coupling capacitance value is like from 10 micro to 1 micro, it is reduced. So as it is saying, the formula saying that cutoff frequency will be increased. So now if I do the simulation also, there is no change in the gain. There is around 42 dB here in this case, and this case also same. And if I go with the lower cutoff frequency is minus 3 dB, 39 or something, so it will be the value 312. So 312. So now if we compare, because of the C value is reduced, right, C value is reduced, I got like a cutoff frequency more. And if you compare these two circuits, right, so the lower cutoff frequency is around 153 above signals are amplified, and this circuit above only 312 signals itself amplified, where my voice signal audible, my voice signal range is around 20 to 20 kilohertz. So this one will be more preferred, means lower cutoff frequency should be as minimum as possible, near to 20 Hz. So this circuit is preferred. So that is how, based on the requirement, based on the bandwidth requirement, and based on the gain requirement, based on the phase shift requirement, we observe that different cases in the C amplifier. In the next session we will be going with the rest of the parameters also.